Our last speaker for this session is going to talk to us about learning to parameterize a stochastic process using neuromorphic data generation. And our speaker today is William. Thank you.
Hi, everyone. Thank you. So I thought to start with an outline. The outline is not a slide-by-slide outline, so don't expect to follow this exactly, but more sort of just the main themes and the main concepts that I wanted to bring across. So first is the motivating question, and that's how do we validate a neuromorphic algorithm is working correctly, right? And in particular, for me, I'm wondering how do we validate a scientific neuromorphic algorithm to see if it's working correctly, right? Is it good enough? Can we trust it? This is a fundamental question that we want to work to address. The answer that's the focus of this contribution is taking a scientific neuromorphic algorithm, a physics code, if you will, and creating an inverse problem from that, and then applying machine learning to solve that inverse problem. The hope here is that we can do that in a somewhat automated fashion without too much domain knowledge, which would be nice because then we can apply that to multiple algorithms, right? We don't want this to be specific to our work. In our case, we use this methodology on a stochastic process called the OU process. We simulated the data on Lehoucq, and then we applied basically off-the-shelf convolutional neural networks to solve that, okay? And then we'll do some concluding work. The challenge that I'm talking about today that we all sort of face in this room is that if we have an algorithm on a neuromorphic system, or we've deployed a neuromorphic system in a robotics application or something like that, there is a fundamental need to know if it's working well, right? How do we test it? How do we verify, validate that it's working? And this gets only worse with an increase in domain applications, right? So the number of domains that neuromorphic systems is targeting is increasing over time. Like we all probably know that. Certainly, if you look in the literature, that's happening. And some of them are traditional, and some of them are non-traditional. The one that I think is interesting and motivating is a strange overlap of different disciplines, and that's using neuromorphic systems for scientific computing or numerical computing. That is solving physics problems, say, on a neuromorphic system. And there are some unique challenges in terms of precision, reproducibility, that we face if we try to go ahead and use something like a Lehoucq to, say, solve radiation transport, right? So suppose you've gone and written an algorithm, like what can you do to really verify that it's doing what you expect it to do? Well, if it's a classifier, then it's not too bad, right? Like we're sort of used to working with classifiers. We can look at accuracy, class average accuracy, F1 score, all these things. If it's a regression problem, we can do absolute error, mean squared error, things like that. If your system is stochastic, as a lot of physics problems are, then it's, I don't want to say it's impossible. It's a lot harder though, right? Suddenly all the things that you want don't necessarily hold true because any given sample could be fallible, right? So what you can do is you can look at proxies like quantities of interest or QOI, and you can calculate that. So for example, if you're interested in how much ice melted or how fast a particle moved or how much, how many x-rays were absorbed, right? All these things can be quantified and you can look at that quantification. But you can easily get into a trap of sort of overfitting your method, right? Your physics portion could not be doing a good job, but you could be really focused on just that QOI and miss the bigger picture. You could instead do a statistical analysis, look at your system, compare its distribution to an expected distribution, and hope that that works out. Or you could do the focus of this contribution, and that's looking at parameter recovery. So what we do in this case is we look at the data that's coming out and we try to predict the parameters that gave rise to that data, right? And so this is learning what's called an inverse problem, and this allows us to sort of increase our confidence in our method by 1 notch, right? This is not going to solve it completely. We want to do all of these things plus more, but each time we add another piece of rigor, we can decide that we're a little bit more confident in the work we're doing. So what I'm going to do is talk about a neuromorphic algorithm that we've talked about a few times before in different venues and publications. And we've gone through these 3 methods. I will first explain the algorithm, and then I'll talk about the 3. I will quickly gloss over the Q of I and the statistics because that's in the literature elsewhere. But before we do that, we need to do some background homework just because I want you all to understand what I'm talking about. So a bit of background. So a few years ago, we had a really nice result where we had formulated 2 algorithms for simulating random walks on neuromorphic systems, right? And in general, we looked mostly at spinnaker, true north, and Lehoucq, but really we just need a basic spiking neuron. One of those formulations used a collection of neurons to represent a walker. The other one, we called it a density method. And the density method is a little different. What it does is you take your physical space, you split it into lots of places, all the possible locations. And for each location, you create a subcircuit. That subcircuit is going to aggregate walkers and then distribute walkers. And so if you can synchronize all of these subcircuits that are all of your locations, you can instantiate a random walk across the space. On the bottom left there, there's a simple 1D to transition circuit for it, but it actually gets much more interesting than that. I'm going to show a quick video of simple diffusion on Lehoucq. That's on the right there. The little red dot represents the walkers. You'll see they're a little spread out. This is just standard Brownian diffusion, so it'll just sort of spread. So the thing that is interesting is this density method, though it's kind of unintuitive, it turns out it has some nice properties that we found. And it turns out that you can do a lot more complicated problems than something like diffusion. So as we started to look into this method, the main pros were that it's really flexible. We can take these different subcircuits and we can connect them essentially in an arbitrary way, and we can have the transition properties be essentially arbitrary. This gives a lot of flexibility, but it depends on the hardware. And since there's no added space cost, there's no added neuron cost for more walkers, it scales nicely in terms of the walkers. But we have to discretize our space, and that causes a challenge. So what we found, though, is that you can, in many cases, or at least in a large family of SDEs, overcome that discretization challenge. And we can not only simulate these stochastic differential equations on neuromorphic systems, but also we can do it in an energy efficient manner. So that's just the plot on the right of one of the results from that paper, where true north and Lehoucq are both much more energy efficient than a traditional random walk implementation on CPUs and GPUs, right? Which is great. Like that's what we're all hoping for as a field, right? That we can do something in an energy efficient way. And more than that, we can do SDEs. We also do other things. We had a nice result where we modeled a steady state heat problem on hardware. And this is the algorithm that I'm going to use as an example, right? So this is the one that I'm going to use to analyze, and we're going to go through those 3 steps of the QI interest, the statistical analysis, and then ultimately this contribution, the inverse problem. Okay. So for QOI on this random walk method, it's pretty straightforward. You can go ahead and calculate whatever it is you're interested in. It depends, though, on your application, whether you're doing radiation transport or financial mathematics, but it's pretty straightforward. And we've seen it's in the literature now. There's a few different papers on it, but overall, we're pretty happy with the QOI estimation. We can, in many cases, estimate the error. We can characterize it. Sometimes we can bound it. Generally, more walkers is better in a square root n sense. And depending on how we set up the system, more time steps means better accuracy. For example, on the right here, this is a plot of that steady state heat equation. This is in simulation, but the analytic solution is the dashed line. And as you see, as we are increasing the number of time steps, we integrate over more and more information, and we pretty nicely approach that approximate or that solution. Like I said, we can also do a statistical analysis, right? So what we've done here is basically we want to take the data that's coming out, all those walkers, all those densities of walkers in the locations, and apply some sort of statistical measure or distance to say whether or not they match what we expect, right? There's a few ways to do this, things like log likelihood ratio or KL divergence. The plot on the right is showing KL divergence of conventionally generated walkers versus Lehoucq generated walkers under a few different parameter sets. The details here are not super critical, but what we see is that Lehoucq is certainly wrong in some cases and wrong by a lot, but the vast majority of samples fall in line with what we'd expect. So it's a little bit unsatisfying because we only have this metric, but like this is still encouraging in some ways. And I know both the QOI and this statistical measure I've talked very briefly on, but I'm happy to point you to where you can find these papers and read all the gory details. So those are the two methods. Now switching to the new contribution that is of the inverse, exploring this as an inverse problem. So when I say that, just to define, an inverse problem is where you're solving for underlying parameters from observations. So in our case, we get our observations from a simulation on the neuromorphic system. And then what we're going to do is we're going to try to recover the underlying parameters using machine learning, in this case is CNN. In a lot of application spaces, this is like an experimental thing, right? Like you have some experiment and you want to figure out what caused that radar signature, say. For us, we're using it to basically somehow quantify that the data is useful, right? That the original parameters are captured by our physical system, which is what you want, right? If a parameter is ignored by your simulation, then it's not being very useful. So with that, we need to introduce the specific problem that we're going to look at. So we focused on this 1D Ornstein-Uhlenbeck process, an OU process. There are some nice properties of this, but I won't get into it. It is useful for many domains, molecular mode of motion, stock prices, diffuses particles, and so on. But our goal is to recover those parameters K, D, and Z, right? Because they define, given this form, they define the action of the physical system. And so those are the three parameters that we want to recover at the end of the day, right? And if we can do that, that says that we've found the underlying system and that our simulation somehow represents that. So here's our overall setup. The left-hand side sort of shows from the perspective of data generation. The right-hand side is from the perspective of network training. There's supposed to be an equation. I'm sorry that that's broken. But basically, we go from the SDE, we discretize it, as I mentioned. We then take that discretization, we implement it in the random walk algorithm that I mentioned earlier. We implement that on Lehoucq. We get lots of data in form of densities over time and trajectories of random walks. And what we do is then we feed that into a traditional CNN. I'll talk about the details in a bit, but that basically maps from trajectories into that parameter space. And that's how we train it, right? Now's probably a good time to look at some data though, because this is fairly abstract. So we're gonna go through some examples of data. It's gonna look noisy because it's stochastic. What we're gonna look at is two samples simultaneously. So the top here will be one sample, the bottom here will be another sample. The y-axis is a spatial coordinate, right? This is a 1D problem. The x-axis is time. So this is showing a trajectory over time. Brighter colors mean more walkers, darker colors mean fewer walkers. And what we're gonna try to see here is one of the parameters that's the easiest to visualize. The top half will go through examples that are low in D. So they're gonna be very tight. There's not gonna be much spread. The bottom half will be going through high D examples. So those are going to be high spread, a lot of sort of diffusive activity. The way we generate our data is random. So we can't like exactly pair the top and the bottom. But what we can do is fix the endpoint. So the endpoints won't change. And we will sweep through the starting point. So those will all match. But the K values are going to sort of hop around. Okay. You can see the different K values by sort of how hockey stick like it is. And I also would like you to notice that the ending position is different and that overall the data is fairly sparse in the time spatial dimension. And yeah, and as you can see, it's fuzzy, it's noisy, especially not for high D values. It's kind of hard to see what's going on as a human that's looking at this, but nonetheless, that is the job we're doing, right? I will just add a quick point of clarification. These units are in terms of pixel location, but there is a mapping to the spatial location, which is not really represented here. But just keep that in mind that these all also have different spatial scales that we, that you can't really see here because they're all fixed to the same pixel grid. Okay, so that's a sample of our data. Our entire data set is much larger than that. We generated two training sets. One of them we call base, which is about 26,000 examples in different configurations, most of them randomly assorted. And an expanded set, which has about another 10,000 samples generated in largely the same way. We have a separate validation set of 3,700 examples. And as a test set, we generate data on MATLAB to sort of eliminate that low E, any low E bias. As I mentioned, as we saw, we can look at them as if they were images. So we treat them as an image. From the machine learning setup, we really wanted to take an approach that required as little domain knowledge as possible, right? So we used off-the-shelf CNNs, we used automated hyperparameter optimization, TPE. We did zero padding. We did very little domain knowledge or tweaking going into that. We train with mean squared loss, but I'm going to report absolute error. And it's a fairly standard training loop. And that's what we need to know before we talk results, right? So here are our validation errors for K, D, and Z. For the three models we use, DenseNet, ResNet, and VGG, under the two dataset conditions, the base and the extended. The larger dataset helps with our error, which is good. It indicates that maybe we need more data. I'll get to that, but that is probably the case. Overall, we can compare these just to the absolute sort of ranges of the values, and these are pretty solid. I will say that some of the feedback that the team had, and in talking to folks, is that we're sort of surprised by the error on Z, especially for the base case. Z is the easiest parameter to estimate in a traditional sense. So it's sort of strange that our errors are so high here, but nonetheless, I'll get to it, but we have some ideas as to why. Here is the same plot, but for that MATLAB generated test data. Okay, the errors are a little bit higher, which is expected, though that represents a domain shift from the low E data to the MATLAB data. So it's not, it's not going to be one-to-one exactly. But we see the same sort of pattern, the same sort of behavior. I think what's interesting is this, sort of massive drop off in loss, particularly with DenseNet. And one thing that can help explain that a little bit is if we look at the training on a more granular level. So here are loss plots for the training and validation losses in the base and expanded conditions for the three models, just going from top to bottom. And it shouldn't be the first thing I see, but the first thing I see is that the spread on the validation set is much wider for the DenseNet and the ResNet and the VGGNet. I don't know why. That's sort of weird, but like that's the first thing I noticed. I noticed that before I noticed just how good it does. So yeah, I don't know why, and that's really interesting. Overall, though, our training losses are pretty good, right? Especially for VGG. So this is telling us that the computational complexity of these models is probably sufficient, right? We probably have a big enough model to solve this problem because the training losses are fine. The problem is the gap between the training and the validation. Because of this gap, we're probably working with too few data points. We may be overfitting, we may be over parameterized, like that's what that's indicating there. But the fact that the training loss is good enough, it says that this is sort of like a solvable problem, right? And so, just sort of to tie things together, we solved an inverse problem. That's neat. It's also a heterogeneous situation, right? We're generating data on the Lehoucq, but we're doing deep learning on GPUs, and they have to sort of interact with one another, which is pretty cool. This has been sort of presented as a method to validate a spiking neuromorphic algorithm. Losses are low, could be better. We use off-the-shelf methods, which is good. But there's an entirely separate way to look at this. You could also look at this from somebody who does deep learning training on simulated data, right? Say scientific machine learning or reinforcement learning. This is also a viable way of generating simulation data for a very low energy cost, right? Generally, if you're training reinforcement learning, you have to run your environment. That can be very expensive. You have lots of examples to run. Or if you're doing scientific machine learning, again, those simulations cost a lot of energy. We know that this method is energy efficient, and this shows that there's a sort of paradigm methodology to use that as training data. So that's neat. And then, from here, one thing that would be really cool is if you could do the learning on the Lehoucq also, or whichever neuromorphic platform you choose. So it would be kind of fun to have both the simulation and the learning component on the same chip working, together. So that'd be really neat. I do want to just do a few things. Thanks to my co-authors, Brad, Darby, Rich. It's been a great team. I want to thank Walker, who's at Sandia, who provided some great editorial comments. Also to Craig and Intel, they've been working really hard to build collaboration and set up larger and larger Lehoucq systems at Sandia in our lab. And we're starting to really see the dividends of having the ability to do large scale neuromorphic simulations. So I just want to say thank you all. And thanks for listening.
Thank you very much. I think we have time for some questions.
Hi, thanks for the great talk. You have 3 domains where it seems like this could be a supercomputing application. Do you have a scalability comparison with classical CPUs, or when neuromorphics might have an advantage in larger domains?
Yeah, so you mean for like the algorithm itself? Yeah. So we have done some scalability studies, right? And the main thing when you're using these random walk methods to solve physics problems is that the accuracy generally has a square root n, where n's the number of walkers error. So that's like the most critical scaling. And for us, we scale much better in walkers compared to like a CPU or GPU. So that's good. Our downside is that we need a number of neurons proportional to the space we're representing. And there may be ways around that. Right now, we're sort of looking at bigger neuromorphic systems. Within a large neuromorphic system, if there's enough space, we have no issues on scaling to that, right? Like we can max out the system and that's fine. The challenge is if we need more than that, we need to think of something clever. Is that okay?
Hi, great talk. I have just a question about the inverse problem. It seems that it assumes that the researcher already knows the parametric form of the governing equation. Is there in situations where the researcher maybe isn't so certain, they're using neural networks to explore a dynamic system, is there any way they can still perform some kind of verification like that? Or is it just kind of like you maybe intimated at the start, maybe just a lost cause?
Yeah, so I think the answer is maybe, right? Right now, from what I'm aware of, methods to also find the form are still early, right? So it's not to say that we couldn't do it or that it's not going to happen, but it's not as well defined right now. It's definitely an interest to the group, and it's, I think, an interest to the people who are working in this area. So I think that's really a direction to go. And there are there should be a possibility of, if you have, say, a neural network surrogate for, surrogate's the wrong word because these are for something else, a neural network proxy for your model, you may be able to parameterize that, right? And there are these like context switching neural networks and things like that. So I think it's possible. I'm not aware of that being really effective just yet.
So we have a question from the virtual attendees. This is from David Wyatt. Have you posted your algorithms or code anywhere that they could be picked up, tested on hardware or simulation to identify flaws and optimize the architecture for dynamic systems?
Yes. So the code for so there's a few answers. The code in the Nature Electronics paper is available. If you contact us, we should be able to share that. The code is very easy to share if you're at a government institution. The code for the steady state heat problem, we have the permissions to release and open source the code that generates the network, which we just need to do. So if anybody's interested in that, let me know and we can finally upload that. That is approved. That is, again, that's just to generate the neuromorphic network. That doesn't include the any of the training or the Lehoucq specific backend stuff. We weren't planning on releasing the CNN code for this, like the machine learning, the TensorFlow code for that. I mean, we could if somebody's interested, but it's pretty standard. It's a pretty standard training with Optuna and TensorFlow with Keras. So. Okay, I'll get you the email. Yeah, it's first initial, last name. Oh, no, the work one's more complicated. I'll get you the email. Okay.
All right, let's thank our speaker. So we're going to take a